we are dealing with some math here, and I want to explain to you, before we get into the new physics, this vector product. And it's probably best explained in more of a three-dimensional picture. So I'm gonna use this as my prop here. But just like the dot product, we write it as the first two vectors, A and B, each being a vector. And instead of writing it with a dot, we write it with a cross, hence the name cross product versus dot product. Okay, so there's the dot product. Okay, and the difference is when you multiply these two vectors together, you don't get a scalar, you get another vector. So that's one of two important differences between the dot product and the cross product, or the vector product. You will get a vector. Now, the definition, kind of like this one here, is that the magnitude of the vector C would be the magnitude of the first vector, the magnitude of the second vector, but then the sine of the angle instead of the cosine. So you can kind of see the similarities. This would be the magnitude. Now, if I were to draw a picture, what does that mean? Well, that means then if I had something that looked like this, say this is vector A, and this, say, is vector B, and this is the angle between them. If you break the vector B into its components, so that maybe you do something like this. Here is how much of B is parallel to A, and here is how much of B is perpendicular. I'm hoping you can see that this perpendicular is B sine theta, where the parallel piece was B cosine theta. That's why, if I come back here to the dot product, if this helps, the reason we cared about the dot product, if you remember, is when we did the equation for work, force dotted with distance, in the simple case of a constant force, is when we wrote it as FR cosine theta, when you put the F with the cosine theta, what you were really saying here is how much of F is in the same direction as R. That's why we wanted the cosine of the angle. The cosine of the angle gave it that. It gave us what you might call in a math class the projection of B onto A. How much of B is in the same direction of A. And so that's what the dot product gives us. But the cross product is the opposite of that. The cross product is telling us how much of B is perpendicular to A. Do you see that in the diagram? And so when you do a cross product, you are taking A and multiplying it by how much of B is perpendicular. Okay? Why would we care about that? Well, we cared about the dot product when we did work. Does this at all sound like anything familiar we just got done doing in the last chapter? Do you remember what torque was? Yeah, the torque was how much of the force F is perpendicular to R, or we wrote it as FR sine of phi, sine of the angle between them. And so thinking of this angle, I know I put it up here as theta, maybe it would be more appropriate to put it as a phi, I'm not sure, because that's what we used in the last chapter there. But going back to our picture of, you know, twisting something, so here's the hexagonal bolt, and here's the wrench, and if you grab it right here, this from the pivot point out is R, and then if you apply a force to turn that bolt, you can think of that force as being made up of how much is perpendicular to R and how much is parallel to R. And the part that is parallel to R does us no good in terms of rotating the bolt, which is why when we go to calculate the torque, it was not just how much force and not just how much distance, but also the sine of the angle. And that's a step up from what we did in 102. In 102, we just did force times the lever arm and we left it alone there. But we didn't really get into the trigonometry that, hey, the angle between F and R may not be as simple as 90 degrees. It may be more complicated than that. And so here we have an example of that. All that then is to say is that teaching you this new math or reviewing this math for you tells me that I should probably writing torque as a cross product. And we didn't do that in chapter 10, but we're going to do it now here in chapter 11. You are going to see torque written as R cross F from here forward. Might as well write it as a cross product. That's what it was. And we just had a lot to do in chapter 10, so we didn't bother to also do the math of vector cross product. And so your author kind of moves it over to this chapter. And that's why I left room in this little box, because I wanted to put that a torque then can be written as R cross F, which of course magnitude-wise is R, F, and sine of the angle between them. And so it's this torque that we get a chance to revisit in this chapter. In fact, I kind of like the way this book is laid out, and why I like the test at the end of chapter 12 is you were introduced to torque in chapter 10. You're going to see it again in 11. You're going to see it a lot more in 12. And so it is one of the harder things of the semester, and you've got 3 chapters and 3 weeks for it to sink in before you hit the test on the material. So you know, I think torque and moment of inertia is a little tough at first, and then it begins to sink in. And that's, like I said, exactly what you're going to see here in these next couple of chapters there. Now, I'm not quite done with this at all. This is just the magnitude of the vector C. Wouldn't the vector C have a direction too? And so C as a vector must have a direction. And so that's why the cross product is a little more complicated, I think, than the dot product. The dot product or the scalar product is just that. It just gives you a number. End of story. But this, we have a number and a direction. Okay, so there's how you get the number. What's the direction? Well, here's the definition. It's a right-hand rule, so it means you use your right hand. Okay? And it works something like this. Adjust your 2 fingers, or some people like to use the index finger and their other 3 fingers, but adjust these 2 to make up the vectors, where your first finger goes in the direction of the first vector, and I won't say second finger, I'll hold up these fingers, okay? So your other fingers then go in the direction of the second one, okay? And if you hold them, then the resulting vector will be the direction of your thumb. So if you do this, so my first finger is in the direction of A, my second finger is in the direction of B. What is the direction of my thumb? Out of the board. And so that's kind of why I like this crazy thing. If we put this white arrowhead as the first vector, and the black arrowhead as the second vector, this one then is the direction of C. And so it's a little hard to draw in a 2-dimensional board. You got to take this in 3 dimensions. But do you see the direction of C would be out of the board? Okay. Now, how do we represent a vector coming out of the board? Yeah, it sounds like some of you have seen it before. Is to represent a vector coming out of the board, we do a circle with a dot. Kind of what an arrowhead might look like. Hopefully you've never seen it. But an arrowhead being shot right at you would probably look like a circle with a dot. And so there is our cross product. This is its magnitude. This is its direction. Now let me switch it around. What if it had been written not as A cross B, but as B cross A? Well, I'll start with magnitude. You would calculate the magnitude of the first, magnitude of the second, sine of the angle between them. Any of this change? No. No, the order may change, but multiplication doesn't matter what order it is, right? In your math class, you call that commutative. Okay, so would the magnitude of the vector be the same? Yes. But what about direction? Yeah, it does change, right? If I take my right hand here, okay, and now I put my index finger in the direction of the first one, and my other fingers, my second, in the direction of the second one, don't I get into the board? Okay, so I get the negative of vector C. And so changing the order doesn't give you quite the same. It gives you the same magnitude, but not the same direction. So here order matters. It's kind of like subtraction. Doesn't it matter which one you put first? It doesn't for addition. Right? 3 plus 5 is the same as 5 plus 3. They commute. But 3 minus 5 is not the same as 5 minus 3. The difference is 2, but one is a plus 2 and one is a minus 2, right? And so they anti-commute is the fancy word. And so that's what these do. They anti-commute. We're not used to multiplication being anti-commuting, but multiplication of vectors is then anti-commuting. So we would get a negative C here for that. So same magnitude, different direction. I don't know if it would help to hold this one up here, but the same thing, right? If I were to hold it up so that I put the white one as the first vector, and then the black one, I get kind of that thing, into the board. And so I'd get a vector into the board. And so negative C would be into the board. How would I represent a vector into the board? Yeah, again, sort of what might you see if you were shooting an arrow away from you. You might see the feathers at the end of the arrow as it goes on out. And so there's how we'll use a symbol in our vectors. Coming out of the board, going into the board. Okay? And so that's this idea of a cross product. Oh, let's see if it makes any sense when we actually try something in reality here. I mean, I said then that your cross product would be R cross F, and what I didn't do purposely was to put an arrowhead over that, because torque now becomes a vector. So let's see. If I take this picture that I have, I guess I'm having the vector R go this way. Maybe I'll draw it over here. So here is my vector R. Where's my vector F? Well, F is kind of like that. Fair enough? All right, well, let's take my right hand here. Let's put my fingers in the direction of the first one and open it up till my finger gets to the second one. And what's nice about the right hand rule is what direction do you do it is under 180 degrees. If you can put your finger in the direction of that one and turn your second finger on that one, more power to you, but most people, I don't know anybody who can open it that wide. So the idea is to open it at the angle less than 180 degrees. So go this way, fingers back that way, and there it is. Okay? And so I'm getting into the board when I do this cross product. So looking at this, I would say the magnitude of the torque is RF sine of the angle between them. And so if I call that the angle between them phi, fine, there's my torque. But what direction is it? Okay, good. So this is into the board, right? Now if we call this the z-axis, traditionally we call out of the board plus z, so I would call this then a minus k hat. That would be the direction into the board, a negative z direction. Why does that matter? Well, look at the torque. Coming back up to here now, I can put vectors on this. I can say force equals mass times acceleration. What this says is the direction of the acceleration is the same direction as the net force. Same thing here. What direction is the acceleration? Same direction as the torque. So what direction do I have here for the torque? Well, we said negative, which is clockwise, right? And so we are saying that if this situation existed, then that bolt would rotate in a clockwise direction. And I think you probably already knew that before we bothered to put all these fancy arrowheads. You would have said, hey, take the wrench, grab it here, push that way. Which way does it turn? Clockwise. Yeah. Right? And so sure enough, it goes clockwise. What we learned in chapter 10 was if it turns clockwise, take your fingers, curl your fingers. That was another right-hand rule. Don't mix these two. But we said curl your fingers. Curl your fingers in the direction it's rotating. That points into the board. So sure enough, something rotating in clockwise is into the board, negative. Just like this cross product is negative into the board. So our torque is in the same direction as our rotation. So you can see, I hope you can see anyways, why we're talking about this mathematics. It's very useful in the physical world. And to be quite honest, I wouldn't be talking about any mathematics that wasn't useful in the physical world here. And so that's why you learn a lot of the mathematics. And the mathematics that is, relevant for us are the things that connect to the world around us. And so these cross products are very, very useful here. And that's one example of how it is. And so that's how your author gets started here. He kind of revisits torque, and he writes it as a vector cross product. And so I'm taking this opportunity here to do it as a vector product. Now, I'll add to this math because just like the dot product, we had 4 ways of writing a dot product. We really have 4 ways of also writing down a cross product. Although I think this one's going to serve us probably the most. This is the one I always think about first. But sometimes this is not the best. So be prepared to look at the other options that might show up. Especially as your education continues. I know that in our engineering dynamics class, the 116, which you guys would be taking not this spring, but next spring, they do a lot of the 4th method that I'm going to show you here. Okay, but for this semester and for this start, we do a lot of this here. Okay, so like I said, there's how you get the magnitude, there's how you get the direction. The other options are the following. The magnitude of C could also be found by just saying how much of B is perpendicular to A. And I'm hoping you're seeing that that's really the same thing, isn't it? I mean, if I combine B with sine of the angle, that is the perpendicular part of it. And it is nothing more than coming over here and saying, let's not even look at the total force. Let's not even look at the angle. Let's just only look at how much of the force is perpendicular. And so there'll be times where that's all we know is how much of the force is perpendicular, which is fine. That's all we need to know. We don't need to know the total force. We don't need to know the angle. What we really need to know is just how much of the force is perpendicular to R. That would be good. I'll even go a slightly different step. Another way of thinking of the magnitude of C is by saying how much of A is perpendicular to B. I didn't really show it in this diagram, but if I change colors, maybe you can see it here. I broke down B into the vector A, but couldn't we do it the other way around? Couldn't we look at A projected onto B? And so if I did that, I might take this vector A, maybe something like this, and say you could think of vector A as being made up of a piece of how much of A is in the same direction of B plus how much of A is perpendicular to B. And so it's really the same thing but looking at the other vector. Like I said, instead of looking at how much of B is projected onto A, look at how much of A is projected onto to B. So in this case, we are essentially grouping A sine theta together and saying how much is perpendicular. Now, just so you don't lose touch by math, because I know sometimes we can get so lost in the math and it can get so abstract that students don't see how it applies. So let me make sure you see this. How would it apply here? Well, what we're really saying is how much of R is perpendicular to F. And I think that one's a little harder to see. Let me do it this way. Let me just kind of take this vector A and extend the line of A for a second. And we often call that the line of action. Because what I can do is I can take R and think about R like this, where this part is how much of R is perpendicular to F. And that works too. Now personally I don't really like it because it makes me think that F is acting over here, and I'm like, well, how can F act over there? It's not even part of the wrench. I mean, F can't, right? I mean, F really has to be right here on the wrench where you're holding it. You couldn't have a force there, but it is the equivalent of that. So in other words, if we had that same amount of force, but applied to a wrench that was over here, it would still be the same thing. So a short wrench, okay, off at some other angle. That's fine. But what's really nice about it is then you've just readjusted this wrench so your force is perpendicular to your lever arm. So we call this then the lever arm, and so this would be, you know, yeah, terrible looking wrench. Well, they're all kind of terrible, so okay, we won't rate them. But it's kind of that same thing. So that's our third way, okay? So like I said, there's four, and I want you to see all four. And I'll review, I think, the three easier ones. This is the one I like to do first. This is the one I like to begin and say, okay, let's do the problems around that. We'll get more sophisticated as we go along. But just think of it. It's the magnitude of the two and then the sine of the angle. Now, if you put the sine of the angle either together with A or B, you get either of these two. And so you've got the perpendicular component of those. And those all give you the same thing. So those three are slightly different, but kind of one and the same here. Each of them only give you magnitude. You got to get direction then by holding up your right hand, which, by the way, little fair warning here, is don't get stressed on the test and be writing with your right hand and holding up your left hand. I have seen that. In fact, I saw that recently last week with my other class. Two people, actually. Fortunately, I was looking at them and they looked up and they laughed. Oh, I know what I was doing. Okay. So, who knows how many other ones were too. But they talked to me afterwards. They go, yeah, I was using my left hand. But don't use your left hand during the test. It's put your pencil down and use your right hand. Unless you're left-handed. Okay? But there's that idea. Well, the last one is a little more sophisticated mathematically. It's nice, because it will give you both magnitude and direction right away. But you kind of also lose the physical picture. So we're not going to do too much of it here at the beginning. Like I said, as you advance, you will do more and more of these calculations. But the last way of doing a cross product is this. I'll put it as vector C, which equals A cross B, can be worked out with the components. So it's kind of like this one here with the dot product. See how we put the x components together and then the y components together? So we figured out the dot product by looking at the x and y components of the vectors. You can do the same thing, although it gets kind of complicated. You write the vector A as AX, AY, and AZ. So there are your three components of vector A. You also write out your three components of vector B. You then put the individual I-hat vectors in the top row, and then you do a determinant of this 3 by 3 matrix. But it does work, and it works really well. And in the special case, where A and B are in the plane, then these two are zeros, and it's actually kind of short. But let's do the general case, and then we'll look at the special case here in just a second. Because you may not have remembered or never learned, and so that's why I'm going to review or teach you, how do you do the determinant of a 3 by 3 matrix? Oh, good. Sounds like some of you know here. You expand it by a given row. Let's expand it by the top row. That's the advantage. Because as you expand it, you would get the I component, the J component, and the K component. So I'll start with the I component. The general method is this. You write I hat, because that is the first in the row. Then you mentally think of drawing a line through that row and that column, and so you're left with just a 2 by 2 matrix. And you do what I call kind of the swoosh thing. And you put the AY together with the BZ. Then since you're going backwards, you put a negative AZ with the BY. Do you kind of see that motion? Go across the diagonal, put those two together, subtract those two. And so that would be your first term. Then you go to the next term. All right, the next term is going to have a J hat. And moving on down, you would then do the final term. But that's how you can get it as a vector. It's got to be term by term. You got to get the I hat, J hat, and K hat. So you could see that the cross product is certainly more complicated than the dot product, because the dot product just ends up with a scalar. That's it, one number. But a cross product ends up with a vector. So we have to have an I hat, a J hat, and a K hat. We have to have all three components. So let's go to the J hat. The J hat, for those of you who may not have seen a determinant, same idea. Think about the J. Maybe I'll change colors if that will help. And cross out that row and that column. So you're left with these two and these two. Do the same swoosh type of thing. Go AX BZ minus AZ BX. Now there is one little subtlety, is we change sign as we go along. So as we expand a determinant, the first one is plus, minus, plus, minus, plus, minus, plus, minus. Now we only have 3, so it's going to go plus, minus, plus as we go through there. So here's the first term, here's the minus for the second term. Well, then we get to the last term, and so the last term will be then a K hat. And again, I change colors, which I guess my only option is to go to the yellow, which I know doesn't show up real well. But maybe it's good in this case, because I want to cross out that row and that column. And then I'm left with this 2 by 2. And so I would have an AX and a BY minus an AY and a BX. And it would be a plus sign. And so that's what we call the expansion here, the determinant of it. You guys seen this? Yeah? Last week. Oh, shoot, I should just skip it then. All right. So you guys already, you've been doing this. All right. So, well, I won't ask. I mean, nobody's seen it, and nobody's going to raise their hand for that one. Okay. but that's this idea here. Now, like I said, this is a little more sophisticated than we really need right now. So I would recommend that we start with this one, and there'll be times we'll look at this. But even when we do look at something like this, most of the time we will have our two vectors in the plane. That is, we will have X and Y components, but no Z components. Look carefully at this result. I want you to see two things. The first one I want you to see is, notice, the X component is not made out of X components of the vector, right? That's this cross product thing. Did you notice that when you take a cross product, the result is perpendicular to the other two? And so if these are in the xy plane, this is going to be in the z-axis, right? And so never would an x component come with x pieces in it. They would have the other pieces in it. Same thing here. Notice the y component has no y's in it. And notice the k component has no z's in it. So the part, if we're thinking of this as a torque, the part that makes it rotate around an x-axis comes from the yz plane. The stuff that makes it rotate around a y-axis comes from the xz plane. And the stuff that makes it rotate around a z-axis, it comes from the xy plane. And like I said, most of what we're going to do is going to be a simple case where our distance and our force will be in the xy plane. If they're in the xy plane, then the z component is 0 and the z component is 0. So that goes away. Z component is 0, that goes away. Kind of makes sense. If you only have them in the xy plane, what's it going to do? Rotate around a z-axis. And so this wrench that I guess I've now erased, but you give me any situation. And if you go out here at some distance and you apply a force, any direction you want to apply a force, or go any direction in the plane and apply a force, what's that bolt going to do? Rotate only around a z-axis. Could be a plus, could be a minus. And you can see that in the math, which one is bigger. And so really, this is the one that's going to be relevant for us. Although these are true, those involve rotation around other axes. And like I said, that's really not the scope of this class. This class is to rotate around a single axis. We usually label it then as the z-axis. So we put our forces and we put our lever arms all in the xy plane, and we get it rotating around the z-axis. That's good for us. In fact, you have a great lab on Monday. I like the lab on Monday. You're going to put an object on this table. And you're going to put some ball bearings down and you're going to put it on there. And when you put it on that table, that means it can move and rotate, but only in the plane. And then you'll start pulling on it in the plane. You'll pull on it here or here. And so what you are going to see as you do the lab is you're going to have your forces in the xy plane. You're going to have your distances in the xy plane. And you're going to see, does it rotate or not? But when it does rotate, it will rotate around a z-axis, because it'll sit on the table like this. And if it does rotate, it will rotate on the plane of the table. So the axis of rotation will be on the z-axis. I guess it'll be kind of like this thing here. It'll be this table, and then it'll rotate. Okay? And so it'll rotate around a z-axis. But it's a good lab to teach you how to calculate torques. That's the point of this. Using cross products, thinking about it in terms of calculating torques. Okay? So that's the end of my little math discussion, my math review, if you will. And also the end of my discussion on how are we going to represent torque now. We're going to write torque then as a cross product. And so now, let's get to the meat of the chapter. What is this chapter about? Well, I said it at the beginning. It is about angular momentum. What is the angular momentum? Well, here is the definition. Hopefully it doesn't come too much of a surprise. It is going to eventually be equal to this, as you guys pointed out. But the definition is simply this. The angular momentum is equal to what? Well, maybe I'll draw a picture. I want you to see how this is going to look a lot like the torque. That if I had, let's say a little axis right here, and I had an object out on a bungee cord, and I'll pick a a bungee cord here, so that at this moment it's some distance r away from this point that I'm going to call my origin, my axis here, okay? But this object, to make it an object, I'll make it a little baseball or softball for us softball players there, okay? And us who are too old to play baseball anymore, so softball here. And then we'll send it out here like this and say, okay, there is its velocity. And if it has a mass, then of course that's its linear momentum. But if you call this angle phi here, we might be interested in not the total momentum, but how much of the momentum is perpendicular to that distance. The part that it would have if it's going in a circle. In other words, if this was going in a circle, then this being r and this being the momentum, the angular momentum then is exactly that. It is the r, how far away is it, and how much of the momentum is perpendicular to r. And does that look familiar to what we've been doing with torque from the last chapter and today? Where torque, we weren't interested in the total amount of force, but how much of the force is perpendicular to the distance, because that's the part that makes it rotate. And this is the part we're interested in. We're interested in the part that has it rotating. So we should write it as how much is perpendicular. And if you do that, isn't that r p sine of phi, right? And so just like the calculations we were doing, this would have the what is r, what is p, and what is the angle between r and p. And in fact, wouldn't that make sense then to label it as a cross product? And so there is our first step in the chapter on angular momentum. Our definition of angular momentum is this. It is r cross p. And that's what I want to put here. And so it is an r cross p. So just like torque was r cross f, angular momentum is r cross linear momentum. Again, it's a cross product, which is why we just spent the last 40 minutes going over what is a cross product and how does it work here, okay? And so that's what we're going to do. And that's where we're going to spend the balance of the chapter. The balance of the chapter is all about understanding angular momentum. So let me give you some examples. The first example is really the easiest one if it's going in a circle. All right, so I'll put up here moving in a circle. Well, I guess I would have my axis here, I would have my string out there, I would have the ball at the end of it, it would be going with some velocity v, it may have some mass, and if it just goes around in a circle, it always has the same radius, and just for simplicity, let's just say it always goes around with the same speed. If I were to ask you, go ahead and calculate the angular momentum, well, what would you get? Yeah, I guess you would start off by saying L is r cross p. And there would be two steps. The first step would be to say, what is its magnitude? The second step would be to say, what is its direction? I'll start with the magnitude. All right? So to get the angular momentum of an object going in a perfectly circle, I guess I would have r. How would you get linear momentum? mv. What would be the angle? Right, it's the angle between r and p, so there's a little right angle. That's why I picked this one as the first one, so it'd be sine of 90 degrees. And so the magnitude of L is mvr. I'll just kind of change the order a little bit since that's kind of how your author writes it there in the book. mvr. And maybe you guys remember this from 102. This is the only equation we gave you for angular momentum in 102. And that was it. It only works when you are moving perpendicular to the distance. And if anybody remembers your 102, you had a problem involving the planet Mercury. And it's usually a tough one, and students come back into class and ask, and because it talks about Mercury when it is close and when it is far, and you got to figure out, and it was all based upon conservation of angular momentum, what we're working towards, if you remember that. But the formula we used was MVR, and that's why the description of the problem of Mercury was something like this. It said, calculate the angular momentum, but they gave you the two special places. Mercury has an elliptical orbit here. So they gave you it here when it was perpendicular, closest spot, and they gave it here at, I may as well do the center of the sun, and then they gave it here at its furthest point there. And that's all you could do in 102, because we weren't using any trig functions and we didn't say sine of the angle, but we used this formula. So if it is a perfect circle, or if it's not a perfect circle, at these special points, apogee and perigee, and I guess I should know which one's which. The apogee, the close one? Anybody familiar with their astronomy? I'll need to look that one up. But the two names of those, the close one and the far one here, are listed there. But they only work at the apogee and the perigee. They don't work at the other places. But now, you're more sophisticated. Could we do it at the other spots? Sure. And so let's get away from a perfect circle. Let's look at an ellipse. And so let's take Mercury right here. And at this place, Mercury would be moving something like this. So this would be its momentum. And its r vector would be this. And the angle between them would be some angle, and in this case, less than 90 degrees. But when you go to calculate its angular momentum, then you would have an MVR, and you would have a sine of phi. Now, so that I don't confuse you, I'll just say it. I haven't proven it for you yet. We soon will. But the angular momentum doesn't change with Mercury as it goes around. That's why we said the angular momentum here and the angular momentum here are the same. I would even go further than that. I would say the angular momentum here, anywhere on this path, is the same. And so what ends up happening for Mercury is, as it goes to different location, its radius, its velocity, and its angle keep changing in such a way that its angular momentum does not. Now, I haven't proven that this semester, but since I brought up the problem from last semester, or 2 semesters ago, whenever it is you took the 102, we used the principle of conservation of angular momentum to solve it. We said that the angular momentum here is the same as here. And it's true. But I would even say it's bigger than that. The angular momentum is the same everywhere along its path. And it changes in such a way that these numbers come out to be the same. That's why as it moves from here to here, its speed increases, because both its r and its angle decrease. And so those two decrease, the other one increases, so the total remains the same. Well, we'll prove that. I think even before today's over that has to be a conservation of angular momentum problem. But I just wanted you to see kind of the beginning grounds here. How do I calculate it in a perfect circle? Right here, or when they're at 90 degrees. If it's not at 90 degrees, I can still do it. I just got to put in the angle for it. It gets a little more complicated. But since it's a vector, doesn't it also have direction? And all I've put is the magnitude of it. So how do I get direction? Okay, here's that right-hand rule here. So let's come back to this circle. If I come back to this circle, let's see. Here's the vector r. It's going that way. Okay, so that means my finger would go this way. My first finger. P is in the same direction as V. So I will hold my second finger that way. Which way is my thumb? Out of the board. So which way is the angular momentum in this problem? circle with the dots, it would be in the k-hat direction, right? Now, hopefully this agrees with the direction of its velocity. What did we do a couple days ago in chapter 10? How do you get the direction of its velocity vector? Didn't we curl our fingers in the direction that the mass is rotating? And isn't your thumb pointing out? Good. So the velocity vector is out. And the angular momentum is out. And so the angular momentum as well as the angular velocity are in the same direction. Just like in chapter 9, the linear velocity and the linear momentum are in the same direction. It's just that it's three-dimensional, so I think it's a little bit harder. But it's definitely out, sure. How about Mercury here? What's the direction of the angular momentum vector here? Okay, well, put my finger in the direction of R. So there's R. There is P. So R is that way. P is this way. Thumb is out. So this one too is out of the board. And that's a k-hat direction. And again, if you were to take your right hand and curl your fingers in the direction the mass is moving, it would be pointing out of the board. Or if you'll just look at it, it's counterclockwise, positive. See, counterclockwise, positive. And so they fit together here. The direction of the angular momentum, the direction of the angular velocity. They go hand in hand. So that's how we get a vector out of this. We do the right-hand rule. Or we look at the direction of the velocity. Or we look, is it clockwise, is it counterclockwise? Those all should be consistent with each other. And sure enough, they are. Now, I guess in both these cases I had out of the board. How would I get into the board? Okay, if Mercury had been, let's say, over here going this way, well, that right away is a clockwise direction. So hopefully you're seeing clockwise, that would be into the board. But if I do it with my cross product, this would be R and this would be P. So let's take my right hand, put my finger in the direction of the first one, put my second finger in the direction of the second vector, P, and my thumb is into the board. So sure enough, it works. And I know this can get kind of tricky sometimes. You gotta twist your hand there and figure out which way. So if you get too tight, there's probably a better way of doing it here. But you want to look at that hand and say, which way is your thumb pointing? And so in this case, it would be into the board. And so I would have a little X there and saying that would be the direction of the angular velocity as well as the angular momentum from that cross product. Fair enough? All right. Get the idea of angular momentum? Because it is going to get a little more complicated. Watch this one. Let's just take an object, nothing around it. No planets, no atmosphere, no magnets, no forces on it. It's moving. Newton's first law says what about it? Yeah, object in motion, what? Stays in motion. Constant velocity, forever and ever and ever. Okay, so mentally, hopefully you see that. This would just keep going like this, and this. Right? What's the angular momentum of this object? Oh, it's so tempting to say 0. But if it was that easy, you know I wouldn't have been asking it, right? I gotta admit, here it is, it's going in a straight line. Doesn't it seem like it should be 0? And it might be, but it doesn't have to be. Let me see if I can take you back a chapter. What if I said, what is the rotational inertia, the moment of inertia of a rod? What would you tell me? Is it 1/12 ml squared? It's not a fair question. About what point? Wasn't it 1/12 around its center? But wasn't it 1/3 about its endpoint? And couldn't we be anything in between there as we apply the parallel axis theorem? So to say what is the moments of inertia, you have to say about what point, right? That's part of this whole idea of this chapter and rotation. Where is your coordinate system? And you're going to see that here. Doesn't the torque depend upon R? Doesn't the rotational inertia depend upon R? And doesn't the angular momentum depend upon R? It depends on where your origin is. In other words, let me pick 3 origins. Let me pick one that is here. So there's number 1. Let me pick one that is here, number 2. Let me pick another one right here, which is number 3. And I claim that the angular momentum of all 3 of those are different. One of them is 0, one is positive, and one is negative. So you can't just stand back and say, what's the angular momentum of something? Now, I got to admit, when something is going in a circle like this, it's kind of implied that what is the angular momentum based upon the origin, and the origin being the center or whatever the object was rotating around. In this case, it's the sun. So without even questioning it, I just said, hey, I'm going to calculate it from the sun. And you went right along with it. When I had a perfect circle, I just did it around the center of the circle. It makes sense. I can't imagine doing it different than that. But when it's going in a straight line, then it's not so obvious where do I pick the point from. And it really illustrates my point that the angular momentum depends not just on the linear momentum, but also on the position vector. Where is it? See, watch this. Let's say we do number 1. Okay? Here is origin number 1. Here is the object way over here. If I were to draw a line out to there, I would call that R number 1. And so when I go to calculate the angular momentum, I would say it is an R cross a P. Its magnitude would be R1mv sine of the angle between them. And so I'll put phi 1 there, sine of phi 1. And so that would be the calculation in terms of magnitude. What direction? Well, there's R, so I'll put my finger, my index finger in R. P is back here, so it's kind of like that. There's R, there's P. Which way is my thumb? Out of the board. And so that is out of the board. And so that is a positive K hat. And so that is what I would call the angular momentum as calculated from that origin. Because look at origin number 2. What is angular momentum number 2? Which I guess I will call R2 cross P. Now, I won't need to put a 1 or a 2 for P, because you just told me Newton's first law, it keeps the same momentum. Okay, linear momentum. But if I were to draw a line out here, wouldn't that be R2? And so it would be R2 times M times V times the sine of? Okay, I'll really go 180. Isn't R that way and P that way? Okay, so it's 180, but the supplemental angle, so if you want to call 0, you'll get it right there. But more accurately, it's 180. But what is the sine of 180? 0. So hopefully that illustrates my point that in the top one, it came out to be a positive number, not 0. This one, it came out to be 0. So does the angular momentum equal 0 for something going in a straight line? No. Just like talking about its moment of inertia of its torque. What is the position of it? It is very important. Okay? Where is the origin? What are you doing your calculation around? What point are you interested in? And so, as we'll see, kind of like energy, it's not so much what is the angular momentum, but how much did it change by? Did it increase? Did it decrease? You know, is there a change at all? And so it's not the value, but the change in the value that's relevant. Because the value could be anything you want depending on where you put your origin. Now I must admit, let's put our origin then at the places that's going to make the calculations the easiest. Don't put it in a hard spot. That's just going to make the problem harder. But that's a skill you got to learn over time. Where do I put it to make it an easier calculation? And I would say probably an origin here makes a lot of sense because the angular momentum is 0, whereas here it's a positive number. Now let's try number 3. And you're probably getting the idea by now that number 3 is not going to come out to be 0. And it's not even come out to be positive. It's going to come out to be negative. So if there is R, the magnitude would be R3mv sine of, and I'll put angle 3, and I guess angle 3 would be this way and back. Oh, and actually that's, I see why you guys said 0, because I wasn't really doing the angle. I guess this is really the angle, and I'm doing the supplement of it. So that's why when I said 180, you said, no, it's 0. Okay, fair enough. But again, they're supplements of each other, so it comes out to be the same number. So we don't have to worry about what side is it. Is it this side or that side? But it's still then hopefully is that same number. What direction is it? Right, I'm going to take my right hand, and if I put my finger in the direction of R, and then I put my second finger in the direction of V, I guess something like that, I get into the board. And so it's negative. And maybe you're just seeing all of this together. If anything up here is going to give me positive numbers, anything down here is going to give me negative numbers, anything along this line of motion is going to give me zeros. And so when you ask what is the angular momentum, it kind of depends on where you set your origin here for this object that's going in a straight line. That's why I was telling you that this can be a little bit harder than it looks at first. Even though it's not rotating, it does have an angular momentum. Now I must admit, most of the time we're going to be interested in things rotating. That's the whole point of the chapter here. But there's somewhat times where it becomes quite useful. Let's see if this helps here. Let's look a little closer at L number 1. What would this together with this be? Do you see it? It's this, right? Can I call this Y number 1? So this is really MVY number 1. It kind of makes sense because think about it when this object gets right to here. Isn't that how you would have calculated its angular momentum when it got there? Its distance would have been y, its angle would have been 90 degrees, and you would have just taken an m times a v and times the y? Sure. Doesn't surprise me. And if you think like maybe there's a little fish hook down here, and so when this thing comes along and gets snagged, what's going to happen to it if it gets snagged? Isn't it going to spin around kind of in a counterclockwise direction? And what's the direction of the angular momentum for that? Positive? And so I know it's not really doing this, but it has the same angular momentum as that. And so if that helps, here's the fish hook, here it comes snagged, and it's going to spin this way. Because look down here, what would happen if you had a fish hook up here and it got snagged? Wouldn't it go this way? And so what's the angular momentum there? Negative. And so I think that will help you visually, so that, hey, anything down here would be like getting a negative rotation. Any axis up here looks like it would get snagged and make a positive rotation. And anything that is along this line of action wouldn't have any rotation. It would just go in and do nothing, or no rotation. And so that's why I get 0 there. So that helps me mentally thinking about, okay, what is my angular momentum? Is it positive? Is it negative? What is it equivalent to? So again, you can probably see this here. If you put these two together, you're looking at this distance, y3. And so you got mvy3, the same number you would get if it went around. Okay? And so there's the idea. All right, so there's our angular momentum, not just for the simple things like circles and ellipse, but even straight lines.
Would you say it would be a
Depends how mathematical you want to be. I would do this. I would say L3's magnitude is that. That's what I would do. That's its magnitude. Then its direction would be in the negative k hat direction. That's what I would do. To me, that's a lot more helpful. Because then I got its magnitude and I got its direction. And those are usually the two pieces that we put together. All right, well, now that you have getting somewhat of an expert with this, I will say, short chapter. This is it. This is the whole chapter. Of course, the first part of this is learning how to do cross products. But watch this for a second. What if I were to put L, which equals to R cross P, and then I will take the time derivative of both sides of the equation. What do I get? Well, let's give it a try. This side of the equation would say dl dt. Okay. But what do I get over here? And I know you've taken derivatives. I know you've taken derivatives of products. Now, maybe not of the products of the vectors, but I think you'll see that this step will make sense. What you do is you take the first times the derivative of the second, plus you've got the second and the derivative of the first. And so isn't that the product rule you learned in your calculus? It becomes two terms. You leave them alone. And in this case, you better leave them in the same order, because remember, we can't switch the order of the multiplication. So I left them in the same order. But here I'm taking the derivative of the second one. Here I'm taking the derivative of the first one. Let's see if we can simplify this. I bet you can figure out that one. Maybe it will help if we kind of review. What's that? Isn't that force? Isn't that how we wrote the force in chapter 9? Instead of writing force equals to ma, we wrote it as a derivative, right? We moved the m back inside in derivative. So isn't this really an r cross f? Oh, that looks familiar. What was r cross f? Torque. So far, I guess what I have is, how does the angular momentum change with time? The torque. This goes back to our chapter that got us started right here. I take this and I say, to make this thing spin, I need to apply a torque. And so I've got my torque. There. Don't want to do that too much, otherwise it'll unwind. It won't be ready for me when I need it here. But that's that first step. This one might be harder to see. What's this one? Maybe I'll start with this. What's this one? Oh, good. I heard somebody say velocity. Good. Do you see the next step? What's this? And I'll help you out back here on this problem. Why did this one come out to be 0? Because these two vectors were in the same angle or And 180 degrees. How do these two compare? Aren't they in the same direction? I mean, isn't the linear momentum just mass times the velocity? So they're in the same. So what happens if you have a cross product where two of them are in the same direction? What's this? 0. Yay, good. Don't have to worry about that one either. So the conclusion is this, that the torque does what? Well, changes its angular momentum. If you have a torque, you change the angular momentum. If you don't have a torque, you don't change the angular momentum. Does this look familiar at all from chapter 9? I mean, chapter 9, didn't we have this? Force is equal to dp dt. And so hopefully you see this connection here. And so the last piece here, I'll put this in here. Force is an indication of how much its momentum change. No external force, then what do we have? Right, no change in momentum. Conservation of momentum. We have the same thing here. If we have a torque equals to the angular momentum changing, and I guess I should put a vector there. And so what we did here in chapter 9 is if the force was equal to 0, what did we say about the momentum? Constants. And this was our conservation of, and I don't know if we used the word linear at the time, now we will, linear momentum. We said the momentum before equals the momentum after. And we did problems like this. We said, here comes a car, it moves along, hits another one. If there's no friction down here, then as a system, the loss of momentum by this one is equal to the gain in this one, so the total doesn't change. Can't we say the same thing here now? And this is the grand finale of this chapter. Conservation of angular momentum. I said it a couple times. We're finally there now. This semester is about teaching you Newton's 3 laws of motion and the 3 conservational. Conservation of energy, conservation of linear momentum, and now conservation of angular momentum. And we see it in the math here. This says if the torque is 0, then what can we say about the angular momentum? It is a constant. That is our conservation of angular momentum. And so that's our main principle that I'm trying to get at. So the angular momentum before is equal to the angular momentum after. Let's see if I can demonstrate that. Let me come back to this linear motion. Now these didn't seem to be level, so it didn't seem, well, maybe that's not too bad. It seemed like this one slowed down quite a bit, but the idea of chapter 9, which had conservation of linear momentum, was to say, if I did something like this, this one's moving and that one's not, then as it would come in as a system, there would be no increase or decrease in linear momentum. This one would lose it, this one would gain it. Looks like it didn't go very far. Let me try the other direction. Maybe it's more downhill that way. Yeah, that looks a lot better. I think we got a little hill to it. But what I want you to see is we're going to be doing exactly the same problems. And so just like I just spent the last chapter 10 saying, hey, when you get to a problem, look at it. And think about how you would do if it was linear motion. If it was linear motion and you say, I would do that with conservation of energy, then do that also with the rotational principles. So everything that has to do with rotation, there was an analogy. Same thing here. If I had one that was stationary and one that was moving, and I put them together, and I was asking what's the final speed, I would have done it here by conservation of linear momentum, so I would do it here by conservation of angular momentum. What I would do is I would put them together. And just like over here, I would say there would be a force equal and opposite on each one. So one would lose momentum and the other one would gain it. Same thing here. When I put these together, there's going to be rubbing between them. There'll be a torque on this one slowing it down. It's going to lose angular momentum. But at the same time, there'll be an equal torque on this one, which will make it gain angular momentum. And so the total won't change. And so let me get it going pretty good. Not too fast because it's kind of hard to get these exactly on top of each other. But you can see what happens. The bottom one lost some momentum. The top one gained it. Total didn't change. Conservation of angular momentum. Now, with that in mind, can get a little trickier here, because what happens if I'm spinning with some weights? Any torque on me? No? Pretty good bearings, right? So I would just keep spinning at the same speed, right? Well, really, it's the same angular momentum. Because what if I pull these in? Let them out. Pull them in. Let them out. Did I change my speed? Did I change my angular momentum? No, why not? Okay, good. So the key here in that whole point of illustrating this was to get you to realize I don't have a torque on me as I'm spinning around. This spins really good, some nice bearings, and it spins around. And what remains constant is the angular momentum. The same thing would have been true if we go back to our linear motion and all I had was an object going like this. We would say it keeps its same linear momentum. But since it doesn't change its mass, it doesn't change its velocity either. But let's look at this one for a moment. Can you keep the same angular momentum and the same total mass, but change this? Can this change? Yeah, that's what makes the rotation a little more complicated. Do you see how I pulled them in? What happened to I as I was pulling it in? What happened to this moments of inertia? It decreased. So what did you notice about my angular speed? It increased, so that the total didn't change. And so the rotational stuff gets, like I said, a little bit more complicated. You can see it on something like this. What if I have something that's just spinning around and then I pull it in? Doesn't it rotate faster? But because I'm pulling it in, and so as it's going this way, I'm pulling it that way. How much torque is that? Zero. Because the angle between R and F is either 0 or 180 degrees. I mean, maybe I should draw a picture here. But the point here is I can have a force on it and yet still not have a torque. And so what I have is a picture of, here's the circle, the center of the circle. Here's the little rubber stopper out there. But if I pull it in here and R is out to there, what's the torque? Well, I guess it's R, it's F, and it's sine of 180 degrees, zero torque. So there's a situation where I have the zero torque. Do I have a force on it? Yes. Which kind of makes sense. Force would change its linear momentum. But I'm not after its linear momentum. In this case, I was after, well, I guess I'm kind of making you watch the linear momentum. But what I'm after is to show you this is a situation, too, where you would have zero torque. Now, it's not zero torque because nothing's tugging on it. This is actually tugging on it. It just happens to be the angle it is. And so here is a case where what will happen is you will have a force, but without a torque. This is what I was saying earlier about the planet Mercury. If this is the R out to there, and the force is always in towards the sun, how much torque is applied to the planet Mercury, or for that matter, any planet? 0. So what would you say about the angular momentum as the planet goes around? It's a constant. So it's conservation of angular momentum. And so that's why I said I'll prove it to you later, and so we're here now later. But anywhere along this orbit, whether it be a perfect circle or whether it be an ellipse, there is no torque. Its angular momentum won't change. Its speed will change, because is there a force on it? Yeah. So you can have a force without a torque. And the other way around, could you have a torque without a net force? Well, sure. I mean, here's a simple case. What if I just took a rod here and I pushed down here, and so let's say we put a nail right there with 10 newtons. And what if I pushed with an equal height above it of 10 newtons? What's the net force on that thing? 0. So does it translate? No, but it does rotate. If you look at the torque here, from here to there, that torque, I'd put my finger down, there's R, close it towards that way. The second one's going this way. So there's my R, there's my F, and so this is a torque out of the board, which kind of makes sense. That's going to make it rotate in a positive direction. But this one too makes it rotate in a positive direction. The R is up. The force is horizontal that way. The thumb is out of the board. So both of these apply a positive torque. So you put those two together, both of them are making them rotate in a positive direction. So this one has a torque but no net force. So it doesn't translate, but it rotates. And so notice that we can have different things. We could have a force without a torque. We can have a net torque without a force. We could have both. That's probably the easiest one to do, maybe the most complicated one to analyze. I mean, what if I just had one force on it? What would that happen to that board if this was floating out in outer space?
Translate and rotate.
Yeah, it would do both, right? It would be a translation and a rotation effect. As we push on this thing's going to go like this, right? It's going to start rotating in a positive direction, but it's also going to start translating. So we've got both a force and a torque. Well, I don't want to get too dwelled into that. You'll see that as we do example problems. But I do want to then show you more of this conservation of angular momentum, because I think it can be kind of neat here. That's why I had this wheel up here with this string on it. Because if I were to pull the string, I'd get it spinning pretty good. And maybe if I hold it like this before I sit down, and so let's look at a vertical axis, you'll see it spinning. Oh, got a message, that's good. But it's spinning this way. And let's call that the positive axis, if you will. So I'd say this is spinning positive. And so right now, if you look at me and the wheel, I have a positive angular momentum. If I turn the wheel over, the wheel now has negative angular momentum. What do I have? Positive. And we have the same positive. So if this is 10, when I turn it over, it's minus 10. So I must have positive 20. Because my positive 20, together with it negative 10, gives me a total of a positive 10 again. And so I keep that same amount of angular momentum. You'll see the same thing in the reverse direction. If I won't bother to, I'll spin it this way. So now, oh, that's the same direction. This one. Let's go this way. I should take this off before it gets caught. Should probably take it off when it's not spinning either. All right, well, I'll just hold it up here like this. But now I would say it has a negative angular momentum. So the system, me and the wheel, have negative. Let's just call it negative 10. But again, probably doesn't surprise you. If I turn it over, it has positive 10. And I now have negative 20, because our total needs to be a negative 10. We go back, and we're back to here. The one I like the most, and it's dimensional, so I don't want to get too far into the multi-axis. But what if I already have it spinning just to begin with and hold it this way? And when you look down from above, you might say it's not spinning. Now sideways you would. So, but looking from an axis above, there's no spinning. So I'd say there's no angular momentum from a vertical axis. If I do this, the wheel has negative and I have positive. Total is still 0. If I do this, we both have 0. Total is 0. If I do this, the wheel's positive, I'm negative. The total is still 0. And so conservation of angular momentum takes place as long as I don't have a torque, which is why this is a pretty good bearing and this is a pretty good bearing, and between the bearings here and the bearings here I have no torque and I can just go back and forth one to the other. My conservation of angular momentum. Now this wheel, oh, maybe I should show you. I would bet you've actually done this in your life probably many times. One in particular is riding a bicycle. If you are riding your bicycle, wheels like this, and so it's kind of spinning like this, how do you turn? Don't you lean the bike? And if you look from above, the wheel would be spinning counterclockwise. So what do? You and the bike go clockwise. You get it straight, you go straight. You turn it this way, and now you turn the other way, right? You can even see that if I were to get back onto the stool and think of this as my bike ride. So here I am, I'm riding along, now I want to make a right-hand turn, so I lean the bike. Done turning, I go straight. Now I got a left-hand turn, so I lean. I want to make more of a turn, I lean more, right? And so I take advantage of the principle of conservation of angular momentum as I ride my bike. And if you like motorcycle stunts, they're really neat to see. They really take advantage of it. I mean, they'll go off a ramp, and the wheels are spinning, and then they'll apply the brakes in midair. Oh, that doesn't do any good, right? They're in the air. It takes the angular momentum out of the wheel, so where does it go? Into the whole bike and the rider. So as they go up in the air and apply the brakes, now the bike starts to do this. And if they do it just right, they'll get upside down. Then they'll give it some throttle. Now the wheels start spinning, the back one only, I guess, but really fast, so much that all the angular momentum goes to the wheel and more. So what happens? It's got to go back this way and then land. So the stunt looks like this: apply brakes, do this, give throttle, come over, and make the landing. And so there's your stunt as you go from top to bottom. Or the other nice stunt is the tabletop, where the rider goes up, boom, wheel is spinning. The rider takes the handlebars and crosses them like this. And so what you have is a wheel spinning in this direction. So to make up for it, the back wheel comes up. I can't let go of this. It's going to fall. Ah, okay, that'll stop it. Okay, but with that wheel still going around, the back wheel will, let's see if I get the direction right. So if I take the wheel and it goes this way, then I want the back wheel, I guess this side. And so it will come over here and start spinning. No, wait. Did I do that right? Spinning that way. Oh, this way. Yeah, okay, so this way. And so we'll be spinning. And then, of course, you can turn the handlebars back and get it the other direction here. And so there's your little stunt. Well, don't try this at home. Same story I told you in 102. What about the cat? Take the cat, hold it by its feet, back down here, head up here, let it go. What does it do? Turns over and lands on its feet. How? It's going to spin its tail, right? And so what will end up happening as you let it go, it'll say spin its tail this way, so its body will rotate the other direction. What if it doesn't have a tail? Do you remember that one?
Spins it back.
Kind of, But you can't have the back legs go a different direction than the forward. You can't have, you know, the back legs go this way and then the front legs go that way so far. I mean, its spine is connected, so it won't go all the way around that way. But it can be multiple axes. Say this is the cat, this is the back, here's the head, here's the lack of tail, here's the front legs going up, back legs going up. I'm going to hold it. Cat knows it doesn't have a tail, but if it twists its upper body this way, what happens to its lower body? It matches, right? It has no angular momentum. So the upper body rotates this way, lower body rotates that way. Now here's where you have to have a very flexible spine, and so humans don't do this, but cats do it well. If you bring it all the way together like this, so head and butt are together there. What if you now take your front legs and roll them this way? What's going to happen to your back legs? Conservation of angular momentum is going to roll it the other way. Now you twist your upper body and upper body. And now you land on the ground. So it's a quick motion of down on the ground here. But you can twist it and never violate conservation of angular momentum. Yeah, now you want to see it, right? I said don't try it. I said try it at home here. Yeah, now you're going to find a cat, cut its tail off, and drop it out. All right. So, but there is this whole idea of this, like I said, conservation of angular momentum. Well, one more, and then we'll get into some example problems. I told you, short chapter here, and we'll just work out some examples, and then we'll get into the last chapter. And the last chapter is even shorter. I mean, if I lecture for more than 10 minutes, that's probably too long. I feel like I have to, so you feel like you get your money's worth. But there's not really much in here. It's best to do chapter 12 by just doing examples. But all those ones I've been talking about have been no torques. Because I was trying to illustrate, if you have no torque, you have no change in your angular momentum. Okay, that's what I was trying to illustrate. But now let me give you something a little different here. What if you do have a torque? Now the easy case is kind of boring. I mean, what if I just take this wheel and I untwist this thing? Okay. And if I just put this wheel and I give it a torque, how can I give it a torque? Will this give it a torque? Force? But torque? Right? It's going straight in. How can I give it a torque? All right, so I've got to have a component that's perpendicular. Okay, so I give it a torque. Now if I do give it a torque, won't that change its angular momentum? Isn't that the reverse of this? No torque means no change in angular momentum. But if you give it a torque, it will change. Didn't it change its angular momentum? Didn't it start to rotate? Okay, simple enough. Is that a torque? Yeah, changed its angular momentum. Well, let's try this one for a moment. I'm going to spin it. And after I spin it, I'm going to let go with my right hand and just hold it with my left hand. And see what happens. Now, before I spin it, I'm hoping it doesn't surprise you too much. I mean, let's think about it. Is there a torque here? Well, again, what axis? So I'm saying right here. Well, this thing's pretty heavy. So from here, if I could measure the torque from this point, isn't this the lever arm? Because isn't the center of gravity somewhere in here? And so if I was drawing a picture of this, where should I put this? Let me put it right in the center. And from your viewpoint straight out, I would say, okay, here's the axis. That's R. Then the thing is pretty heavy, so there's an mg. Is that a torque? Sure. R cross F. The force is coming from gravity once I let go of it. Okay, so if I take my right hand, I would say, okay, put my finger in the direction of R, my second finger in the direction of the F, that's down. Which way is the torque? Out. So I'll put a little dot with a circle and say, okay, there's the torque. Now the torque is positive, so that would make it have a change in its angular momentum in a positive direction. And isn't that what you see? Don't you see when I let go of it, doesn't it rotate in a positive direction? No. Is that a positive? Yeah, that's counterclockwise, right? So there's my rotation. I would say this is just like taking the planet Earth and putting a ball up here, and if you let it go, there's a force pulling it down, so guess where it goes? It goes down, right? So this applied a torque in the positive direction, so it rotated positive. This had a force down, so it moved down. Let me change it a little bit. What if this ball was moving already that direction and I applied a force that way? What would that do to the ball? Do you remember this one? Doesn't that make it turn? Wait a minute, isn't it the same force? Isn't it the same force in the same direction? But instead of going down and going faster, what happens to that ball? It turns, all because the initial velocity is different. Do you see that? Because I want you to see it's the same as, isn't it the same force? Same direction? But now it has an initial velocity? So what does it do? Instead of falling, it turns. And so isn't it the same physics? But one's rotational motion instead of linear motion? No? Yes? And so let's see if we can write out the vector here. But I think it is a bit surprising. That's why I wanted to say. And this is the whole theme of these last two chapters. How would you have done it for linear motion? Do the same thing for rotational motion. And so if I was analyzing the Earth and a force of gravity, I would say if the ball's not moving and it's pulled down, there would be a force pulling it down, and so it would move in that direction. On the other hand, if it is already moving, I would say the force is equal to its change in momentum. So that means if it already had an initial momentum this way, the change in momentum would be this way, and so the result is a turn. It is something different. It is not just straight down. Same thing here. If I start with this wheel spinning, so in this case, if you noticed, I spun it like this. So if I take my fingers and curl it, doesn't it have an initial velocity this way? And so now I would take this and I would take this big wheel here and say it has an initial angular momentum. Let me draw it over here. There is my initial angular momentum. Which way is the torque? It's the same direction, right? Just like the same direction, the force of gravity, whether the ball is initially moving or not, the gravity force is the same. And I say the same thing. This was the torque when it wasn't rotating. It doesn't matter if it's rotating now, it still has the same torque. And you said it was out. And it's hard to see in this picture, but if I draw a vector this way and another one coming out, the result would be this way. It would be a turn. And so just like this one results in a turn because of the initial velocity added to it, this one results in a turn. And so as I'm spinning it, once I let it go, it'll now turn to here, which will then turn to here, which will then turn to here, and then turn to here. So I'm using that same torque to make a turn instead of the torque to make it fall. I wonder if that's fast enough. Maybe I should get the string back up. That's fast enough. And so there you can see it. And it's just kind of neat to watch. And it's the same idea that you learned riding a bike when you were 3, 4, 5 years old. You know, it's like, okay, I got to ride a bike. And I'm sure many people told you, and I did this with all 3 of my kids. I said, look, if you will just pedal faster, you won't fall over. Of course, and all three of them look at me, you're crazy, Dad. I fell back there and it hurt, and you want me to go faster? There's no way that's happening. But really, if you go faster, it's easier to stay up. And so that's what you're watching here anyways, is the physics of that, the balancing of the wheel spinning. All right, well, let's do our examples here. Let me turn to the end of the chapter. What's this? Chapter 11. And as I told you, it's not long, but the angular momentum is, a bit more sophisticated, if you will, I think. A bit more complicated in terms of doing the calculation. So we've got some good ones to do on here. I'll jump here to what I got first on my list. It's number 25. It's a black problem, so it's supposed to be an easy one, and I think it is. It's okay, let's look at our new found idea, cross products and angular momentum. So what does number 25 say here? Number 25 just says this: you have a particle of mass 0.5. Now, let's be careful here. It says particle. How big is this thing? Yeah, small. Don't worry about its size. Remember, this whole last chapter 10, we finally learned to give sizes to our object. Well, I guess we did that in the second half of 9. And giving it size, we can have rotation. So we need to start asking ourselves, does the object in question need to be considered a point object? Or does it need to be considered having size? I mean, everything in reality has a little size to it. But some things can be small enough that you're saying, don't worry about its size. It's really small compared to the other dimensions in the problem. And I think that's why the author has said it this way. He says, look, you have a particle of mass 0.4. So it's really small. Okay, you can think of it as a point. It is attached to the 100 centimeter mark on a meter stick that has a mass of 0.1 kilograms. Okay, so the description so far is this. I've got my meter stick. And at the end of the meter stick, the 100 centimeter mark, so this being the 0 centimeter mark, there is a blob that is pretty small. It's a particle right here. 0.4 kilograms. Now the meter stick itself is 0.1 kilograms. So I think in this description, the first thing I hear is they want me to think of that blob as just being a point, all of it at the 100 centimeter mark. And in reality that's not true, but maybe it's between 99 and 101, there, so it's just kind of this blob there. But the meter stick, I don't think they want me to think of as a blob. The meter stick has size. It's a meter long, right? And so that's why they've given me these two. All right, where was I here? 25. So a particle of mass 0.4 kilograms is attached to the 100 centimeter mark of a meter stick of mass 0.1 kilograms. The meter stick rotates on a horizontal frictionless table. Okay, so in my picture, the whiteboard is the table. We're looking down, there's the table, it's spinning on a horizontal surface. Okay, so you're looking down on it. With an angular speed of 4 radians per second. Okay, so this thing is spinning around at a speed of 4. Calculate the angular momentum of the system when the meter stick is pivoting about A, a perpendicular axis to the table through the 50 centimeter mark, and B, a perpendicular axis through the table at the 0 centimeter mark. Okay, so there's two parts to this. There's a part A and a part B, and they have a different axis. And this will also illustrate a point I was trying to make about a half hour ago, is doesn't the angular momentum depend on what axis you are discussing? And so hopefully you will see that here. So I'll put A here, and I'll put a little dot at the 50 centimeter mark with kind of a circular arrowhead saying this is what they're saying. This is its angular speed. Its angular speed is 4 radians per second, about an axis perpendicular to the table. So again, it's three-dimensional, so this pen would be the axis like that. And so that would be the picture in A. B looks similar. still got our blob out here, but now we've put our axis at a different location, even though it's still rotating at the same speed. And hopefully won't be a surprise to you that, no, this won't come out to be the same angular momentum, right? Will not. So let's do a calculation. Well, this opens up the gamut here of, wait a minute, how do you want to do this? Because there's two ways of doing it. But this seems to make the most sense for this one. Which is why I picked this one. I did a lot already on this one. But I haven't done anything with this one here. And this makes sense because this is the rotational inertia. And I just have a rod and a blob. And I can figure out those. That's what chapter 10 was about here. So let's see if I can calculate those. I'll start with that first step, I total. Because I total is going to be the two objects. One of them I would call a rod, and the other one I'd call a little particle here. That little point particle at the end. And that's what I wanted you to see here. I got to get what is the rotational inertia of this. And so this really goes back to chapter 10. It's actually the chapters you're doing the homework on, so it's a good one to illustrate here. How do I get these? Now, I've already done for you in class, and you can go back and look at it. I'll ask if you remember. Do you remember what is the rotational inertia of a rod about its center? Yeah, about its center is 1/12 ml squared. And so there is my first step. In fact, I'll even put in the numbers here. There's the 1/12. The mass of this rod is 1/10 of a kilogram. The length of the rod is 1 meter. So the rod itself, if I grab my calculator here, is 0.1 times 1 squared divided by 12, 0.083. 0.0833 repeating kilogram meters squared. So there's the rotational inertia of just the rod by itself. In fact, that's pretty close to the number you guys had for that disk. I was asking you, 0.009 is what we were looking for in lab there. The other part of this is then this blob. Well, that should be the easy one. It goes back to, again, chapter 10. Remember, I is the sum of MIRI squared when you add up your pieces. In this case, I just have one piece. And it's just one little blob at some given distance. So that hopefully is easy. The mass of it is 0.4. What's the distance away? Okay, 1/2 meter. Or as you said, 50 centimeters. Okay, so 0.4 times 0.5 squared is 0.1. Oh, I guess I didn't need a calculator for that one. But there's the blob. So the total of these two is 108,333 kilogram meters per second. So there's the rotational inertia. So that's half the problem, but it can be a challenging problem. That's why, again, I like this chapter. It forces you to do and use those hard pieces of chapter 10. And then, like I said, you're probably even still struggling with those. How do I calculate the moment of inertia of stuff? But that's how you do it. You take the two things and add them together. What is the rod? What is the blob? Now we can actually do this problem. Then I would say L is equal to I omega. And this is really the easy part. This is a plug and chug one at this point. You've got 0.108333 kilogram meters squared for the moment of inertia. And then the angular speed was given to you as 4 radians per second. So let's see, I guess 4. It's 0.4 and then a 32 makes it a 33. And I'll just do that. And another reason I picked this is the first real calculation. What are the units here? What are the units for this angular momentum, this new quantity we learned today? Okay, so there's the kilogram, there's the meter squared, because that was the unit for rotational inertia. And then there's the per second. What about the radian? right? We add that, throw it away whenever we want. It's not a real unit. We talked about that in chapter 10 there. So there is my unit. And it doesn't have its own little name. It's not named after some great scientist in the field. So, bummer. Might make it a little bit easier to call it something. How about we call it a Santa Barbara City College unit there? Yeah. So we'll make up our own there. No, but it doesn't have one, so we'll just put it there. But notice it is not a Newton. However, a lot of students put Newton for that. What's a Newton again? Yeah, it's only 1 meter upstairs, but 2 seconds downstairs. I think that's why they see that as a Newton there. They kind of mix that. It's not a joule either. What does a joule need? Yeah, a joule does have the 2 meters upstairs, but it also has the 2 seconds. It doesn't have that either. So it's its own unit. It's its own quantity. It just doesn't have its own fancy name to it. Okay, and so that's the angular momentum for A. Oh, and then real quickly B, and then we'll do the rest next time here. But what is the angular momentum here? Well, for this one, it's the same song and dance, but we're at a different axis. We now have the 2 objects. One is the rod, one is the blob. So I'll do the rod. You might remember it was 1/3 ml squared. The blob is still 0.4, but I'm also hoping you remember or see that it is now a whole meter away. And so when I put in my numbers, I go 1/3, I go 0.1, I go 1 squared, I go 0.4, I go 1 squared, and so this is, let's see, 0.1 divided by 3 plus 0.4 times 1 squared equals, and it's 0.4333. In fact, it should be 4 times that one, because I've basically doubled the distance, and it's doubled squared. And anyway, so it should be 4 times more. And so sure enough, it is. And then so the angular momentum would then be the 0.433 kilogram meters squared, and then the 4 radians per second, and so that should be 4 more. So what's that? A 1733, something like that, if I did my math right quickly. And so there's the rotational inertia. The angular momentum. And I guess technically we should have direction, but I don't think we can really answer that because they don't say what direction it's rotating. So if it is rotating the way I've indicated, it would be a positive z direction. And so that would be its direction. All right, well, good. Have a good weekend. Remember, Friday is a holiday, so there's no MC. So if you want to find Dawn or whatever. And of course, remember where you are in life, there is no such thing as a holiday. That's a catch-up day. I don't think I ever told you this story, but I remember after graduation, and I was working for McDonnell Douglas, and had just finished in June, got the job. 4th of July came along, and I got up a 4th of July morning, and I didn't know what to do. I don't know if that was a good sign or a bad sign, but I was like, wait a minute. What do I do? I don't have homework to do. I can't go to work. They're closed. So I discovered bike riding then. Okay. So